Okay, get started. Thanks everyone for coming to this afternoon's session on polygenic risk scores and what it means for the Genetic Testing Moratorium. My name's Stuart Mainland. I'm the appointed actuary for Westpac Life, and I'm pleased to be chairing this session today. Everyone in this room, I think, will be well aware of this topic. We had a plenary session on this the last time we managed to do all of this face-to-face 3 years ago. So this has been a big topic for some time in the industry. The prevalence and ease of access to people's own genetic profiles clearly poses something of a risk and a challenge to us in the life insurance industry. And today's session talks about those challenges, but also brings to the table some new research that RGA has performed in conjunction with King's College London, testing and modelling outcomes around those risks. So I think this is a really fitting topic for the theme of the summit, getting closer and thinking bigger. So we've got two presenters today, and I can definitely count. We've got one here and one on the line. So our first presenter here in person is Scott Mackay. So he's currently the head of pricing for RGA Australia. That's a role that covers both retail and group pricing. He started his career in a graduate pricing role in Scotland almost 20 years ago, and he's gained valuable experience in a variety of roles, including consulting with PwC in the UK and here in Australia, and also valuation roles with Suncorp prior to joining RGA in 2014. Scott has a Bachelor of Science degree in Actuarial Mathematics from Heriot-Watt University and is a Fellow of the Faculty of Actuaries. Online and joining us in a few minutes is Richard Russell. So Richard is the lead health data scientist in RGA's Global Data and Analytics Department. Richard provides specialist resources to enhance RGA's mortality and morbidity modelling capability, including underwriting manual research, actuarial pricing, and innovation projects. He's also a key member of RGA's COVID-19 modelling group, tasked with measuring and forecasting the impacts of the pandemic on RGA's business. Richard joined the company in 2013. Prior to this role with RGA, Richard was a postdoctoral research fellow at City University of London and at Moorfields Eye Hospital, London. Richard received a Bachelor of Science in Biotechnology, a Master of Science in Bioinformatics, and a PhD in Statistics from Imperial College, London. He's authored more than 30 peer-reviewed articles for journals such as The Lancet, BMJ Open, PLOS One, and Annals of Actuarial Science. I'm keen to also note that for Richard, it's 6 o'clock in the morning and it's a public holiday for him, so he's been very gracious in giving us his time over here in Australia. I also just want to make sure that he knows that although he's going to hear Scottish accents, plus his own, and we're doing these questions virtual, I promise him there's definitely some true blue dinky-die Aussies in the audience, plus other nationalities. This isn't just an elaborate hoax. For questions, I think you're all probably used to hearing this spiel by now, but you've got a QR code on your lanyard. You can also ask questions via the app. So please be sending those questions in as we go through the session. And with that, I'll hand over to Scott to lead us off.
Thanks, Stuart. Good afternoon, everyone. It's a pleasure to be here today to talk to you about the ever-changing world of genetics and what this means for the life insurance industry. Okay, so in terms of areas that we want to cover today, I'm going to take you through a bit of a brief history of genetics and insurance over the last 20 years. I'll then hand over to Richard, who will take you through the concept of polygenic risk scores. He'll also take you through some research that RGA collaborated with King's College London using a really excellent data source called from the UK Biobank. We'll then close with some key messages and some risks of anti-selection potentially for the life insurance industry. Okay, so let's get into it. Okay, so one of the key drivers for the development of genetic science is the staggering reduction in the cost of sequencing the human genome. So in 2003, the first human genome was sequenced, and it cost $2.7 billion and almost 15 years to complete. Roll forward 4 years, and that picture of the man there is James Watson, and his genome was sequenced at a cost of $1 million, and he was one of the first people to have their genome sequenced. And for those of you who aren't aware who James Watson was, that he's one of the team that was awarded with a Nobel Prize for the discovery of the double helix DNA structure. Roll forward 4 years again, and that man there, you should recognize him, is Steve Jobs. And he had his genome and his cancer sequenced, becoming at the time one of only 20 people to have their genome sequenced. 2015 comes, and the cost is now $1,000 to get your genome sequenced. So it's a staggering decrease. And by 2018, some providers there were offering genome sequencing for $200. Now, that was a bit of a marketing ploy, but I mean, it shows the decrease and the staggering decrease in the cost over a space of 20 years. Roll forward to 2022, and the cost is sitting around about $600 to $700 to get your genome sequenced. So the availability to the public is becoming wider and wider, and more people should be able to have access to have these tests done. Now it's not just the cost that's reducing. Techniques are also continuing to improve. So up until 2022, genomic profiling only covered about 92% of the total human genome sequence. However, within the last couple of months, they've actually managed to find that last piece and solve that last piece of the puzzle, and now able to sequence the whole genome. So it just keeps developing, and it's going to be more and more accessible to the public. So what's causing this stark rate of acceleration in the public's ability to access genetic testing? Well, governments are investing heavily across the world with a way to improve, I guess, the healthcare outcomes for the population. So right here in Australia, the Australian government launched Genomic Health Futures Mission. I think they could have worked on the name, to invest $500 million in genomic medicine research over a 10-year period. Now, this entity supports research to improve testing and diagnosis for many diseases, help personalized treatment options to better target and improve healthcare outcomes, and also to reduce unnecessary interventions and health costs. So you might hear a term called precision medicine, and it's kind of targeting, coming up with better outcomes and not just using one drug for the same condition. It's kind of trying to find that right drug for the specific person to treat whatever condition that person may have. And in March this year, the government also announced its intention to establish a new agency called Genomics Australia. And that's to support the integration of genomic medicine as a standard in Australia. So Genomics Australia work with consumers, healthcare providers, researchers and industry to kind of take what's been the research work into, I guess, into what we see as we go to the doctors. And once it's established, it will also advise the government on the operation of that $500 million 10-year genomics mission. So the previous entity was all about research, and this entity is really about how they take that research and bring it to, I guess, the public health services. Now, it's not just in Australia this is a focus. Around the world, there's huge investment in genomic medicine research. Genomic sequencing is rapidly transitioning into clinical practice, and implementation into healthcare systems has been supported by substantial government investment totaling over $4 billion in at least 14 countries. Now, on top of that, one of the largest countries that are investing heavily in this market is China, and they're committed almost $10 billion on the China Precision Medicine Initiative to, again, build out great healthcare outcomes for their population. So it's clearly an area with heavy investment, and I guess with that investment, we would expect more progress, development over the coming years. Okay, so I guess given the considerable pace and advancements in genetic science, there's been also a large amount of interest in the subject from governments and regulators. And this slide is trying to give a flavour of that. So there was a paper from the Council of Europe back in 2016 that talked about the ethics and regulatory issues around the genetics and insurance. They concluded that insurers shouldn't be asking for the results of genetic tests for insurance purposes. Now, some of the European countries adopted this stance, so France, Austria, Belgium, Portugal. However, others, such as Germany, put in cover limits as to when disclosure of genetic tests are required. And in 2019, we saw Australia bring in a moratorium on genetic test results in insurance for cover up to $500K for death and TPD, $200K for trauma, and $4K per month for IP. And in late last year, Singapore released their moratorium, and that prevents life insurers from using the results from predictive genetic tests and under certain cover levels. And something else the FSC have done from the start of 2021, the Australian life industry has been collecting genetic testing data as part of life insurance applications for the specific purpose of, I guess, for monitoring the ongoing effectiveness of the moratorium. And then in February this year, they've released their first findings from this data. So when I seen this, I was quite taken aback, actually. There was over a 6-month period to June 2021, there was close to 850 applications for cover, which included results from a genetic test, which in my view was quite high. Of that, 77% of those applications, the genetic test result had no influence. 13% were positively influenced with a favourable genetic test result, and 9% had either no terms offered because of the result, or it might have been loaded or been an exclusion in there. So the FSC are planning to review the moratorium this year. It's going to be, I think, towards the tail end of the year, with the revised guidance on what will happen beyond June 2024, that's when the current moratorium is due to end. Okay, so before I hand over to Richard, I just want to talk about briefly why do we think that the life insurance industry currently doesn't worry about the genetic anti-selection risk. So we think the main reasons are, firstly, genetic risk information will not be widely available in the near future. Now, given what I've just talked about, I'm not sure that is the case. Number two, monogenetic mutations that indicate significantly higher risk of disease are rare, and therefore the cost imposed on insurers by any associated adverse selection is deemed small. So Richard will go into more detail on that. Most common diseases are multifactorial, and the genetic contribution to these diseases is modest. So that's saying genetic testing won't help us identify the high or the low risk groups for most common causes of illness. Number four, genetic tests will not deliver significant risk information that is not already available from traditional biometric measures used in underwriting. And then finally, number five, the genetic contribution to disease is adequately captured by family history. Now, The aim with this presentation is to challenge or confirm these beliefs or assumptions. So with that in mind, I'll hand over to Richard, who will take you through the next part of the presentation. Over to you, Richard.
Thank you, Scott. And thank you for the introduction. I'm pleased to learn it isn't a hoax. That what did cross my mind at one point. So Scott put on screen there those questions and those beliefs. I'm going to give you a whistle-stop tour of some of the science and the research that we've done with King's. But the paper that we published on the subject is out. It's in the Annals of Actuarial Science and published in 2020 and in print just a couple of months ago, actually. So just a quick bit on the science then. So Scott talked about the genome being sequenced. So there's the DNA helix structure discovered by Watson and others. And a human genome is about 3 billion letters long, 3 billion base pairs long. And that's packaged into chromosomes and genes. But then scientists have been sort of investigating how the genome differs from individual to individual and the variation in those letters. And by far the most common variation that we see is something called a single nucleotide polymorphism. It's where a single letter in the DNA genome sequence is different. So in the example here on screen, we've got a cytosine and it's been mutated to a thymine here. So we've known about these polymorphisms, these genetic variations for a while, and scientists conduct something called a genome-wide association study to look for SNPs and other variation between individuals. And in particular, if you are interested in what genetic component there is to disease, you would sequence, using this genome-wide association study, people with the disease and without the disease. And then you'd use these DNA microchips here that can tell you exactly where those polymorphisms could exist in the genome. And this technology is really cheap. So this isn't whole genome sequencing. This is something that costs $50 US, actually probably less than that these days. And it's exactly the sort of technology, excuse me, it's exactly the sort of technology that 23andMe and other D2C test providers use to sample your genome. And when you do that, if you sample across millions and millions of nucleotides, millions of base pairs, what you tended to do in the past, or genomic scientists tended to do, was say, well, we're testing millions of points in the genome, so we'll have to make the p-value very, very strict, have a really small p-value, and we'll just look at the points in the genome where these polymorphisms are above that threshold. So here on the graph, you've got some points at the top there, but we're ignoring all the other kind of points where there is a difference. It's just not deemed to be significant with that very high threshold. What we know now, though, is that when it comes to kind of genetic mutations and prevalence of disease, actually these diseases that we call Mendelian in nature, which are characterized by sort of single mutations, things like Huntington's disease, they confer very high penetrance. That means if you've got that mutation, you've got a very high likelihood of contracting that disease in your lifetime. Huntington's, if you've got the mutation, it's 100% penetrant. Things like breast cancer, there are certain mutations in the BRCA1, BRCA2 genes that confer maybe as high as 60 or 80% lifetime risk of breast cancer. But those genetic mutations are very rare. What the GWAS, those genome-wide association studies, are telling us that there's actually these single nucleotide polymorphisms that are incredibly common. We see them a lot, but they're very low penetrant. If you have that particular one letter change, the chances of developing a disease in your lifetime is very small. So focus, I would say, in kind of the last 10 years or so has turned from sort of studying Mendelian diseases to studying these nucleotide polymorphisms, and in particular polygenic risk scores. Because if we return to the same sort of plot and slide as before, I mentioned that we kind of see lots and lots of these variations. We just previously would say, well, we're only going to look at those really significant ones. What polygenic risk scores is, they say, actually, let's relax the p-value, let's increase the p-value slightly, and instead of kind of just looking at points above the dash line, look at everything in that yellow shaded area. And then the maths is very, very simple. If a particular polygenic risk score confers a 5% increased risk or a 10% lower risk, you just add them all up. And you normalize it, and you get to some sort of polygenic risk score, which might be between 0 and 100, but is kind of adding up all that very common variation that we see to develop just a single metric of risk. So these have existed for a while. So I'd say the seminal papers that developed polygenic risk scores were from about 2015 and 16, and they're the ones I've listed in the table. And as I say, the risk score it's a bell shape, a normal distribution. There will be some people at the top end of the distribution where the risk is higher of developing a disease, shaded red here, and there'll be some people where the risk is much lower than the average, so that green area there. And what these papers and how I've summarized it is just to say, compare people with the high risk in that top 20% with people in the low risk group, the bottom 20%. And you can see immediately for, these common diseases listed, coronary artery disease, diabetes, stroke, cancers, that, these polygenic risk scores do a pretty good job of differentiating risk. So just taking the top study here, it's saying that just based on 50 SNPs, 50 single nucleotide polymorphisms, you can differentiate the risk between that top group and bottom group twofold, and you can see for yourselves that there's even higher risk for some of the other diseases and scores. So they sort of, were introduced to us in the last kind of 7 years, but the literature is frequently increasing. So I did a search just at the start of the month, and there was about 4,000 papers now on PubMed that have those keywords in it, polygenic risk score. And about half of those results were published in 2020 and 2021. So here's one of the papers that was in the table earlier, a study by Abraham and colleagues, and they looked at a polygenic risk score for heart disease, and they looked at people with the low risk there in green and the high risk in red, top and bottom 20%. And then they developed the risk score, but importantly, they controlled for its predictive performance alongside the best clinical risk factors. So this isn't just genetics, it's taking family history, it's taking BMI, blood pressure, cholesterol, and it's saying what is the predictive performance of a polygenic risk score after you've controlled for that information. So really important for kind of, when we think about these things in underwriting and how much extra risk there might be. And in the graph here on the right, what we're looking at is absolute risk. So in that top or in that worst risk group, the red line here, 10% of men who are in that risk group have developed a coronary event by age 51 years of age. And in the green group, the lower genetic risk group, it takes until 63 years of age on average for 10% of them to develop a coronary event. So as I said, these have been upon us for a while, and I think what's happening at the moment is some of what Scott spoke about, which is this translation of this great science to clinical medicine. And so this for me is a particularly interesting field here, is taking polygenic risk scores for cancer and saying, actually, we can segment cancer risk much better if we know someone's polygenic risk score, in this example for breast cancer. So the lines are all different percentiles of the distribution of polygenic risk. And then we're again looking at how long it is, or the typical age, average age of a woman to develop breast cancer over a 10-year period. So women in the top 5% of risk, so worst genetic risk, on average, getting to the average kind of risk level by age 37, and women in the lowest risk group never actually reach an average level. So what is interesting about that is you could take this information, therefore, and say maybe we should personalise cancer screening, mammogram screening according to an individual's risk. In particular, you might focus more frequent screening, and certainly I'd argue for earlier screening of these women in the top percentiles of risk, and because they're reaching average levels much sooner than other risk groups. So we've had our eye on these, I'd say, since about 2015-16 in RGA, and we reached out to a Professor Catherine Lewis at King's College London and spoke about the subject, and she's an expert in the area and has developed software to help analyse and compute these polygenic risk scores. And Scott also mentioned the UK Biobank, and it's studies like the UK Biobank and data sets like the UK Biobank that are fueling the research as well. So this is UK study. It asks people of age 40 to 69 to volunteer to take part. And the picture on the left here is they asked them to take part, and they recruited them from 2006 to 10. But at the time, genetic sequencing costs were still very high. So instead of doing the sequencing there and then, they froze their blood samples, and then 10 years down the line, when this became much cheaper, and even today, they're doing more sequencing of these individuals. So very clever, really, clever foresight, because what that meant was we've now got their genetic data, we've got all their data that happened at recruitment, nurse exams, biometrics, self-reported lifestyle questions, pretty much everything you could be interested in on these individuals. And now we have almost 20 years of follow-up on these individuals, and we've linked their data, phenotypic genetic data, to outcomes. So linking it to death registries, disease registries, hospital data, and even GP data. So we asked Professor Lewis at King's, could we further study these polygenic risk scores, and could we kind of have a proxy for underwriting of the individuals, take their lifestyle data, take their lab data, and kind of put them through an underwriting process. So we checked for any kind of prevalent disease in their medical records, or that was self-reported, and then we said, actually now we can kind of control for all the typical risk factors we would do in underwriting, and say this person would be standard risk for a life insurance policy, and then there were people that would be rated or declined. And then we can build another prediction model by group, by the total population, or by the standard groups. And again, control for all the typical things that we would do. So age, gender, smoking, family history, biometrics, but we can also fold in the genetic risk score. So again, we can kind of question some of the beliefs that Scott mentioned. And what we saw, looking at breast cancer firstly, so just looking at women in the cohort of which, after some data cleaning, there was 200,000 of them, and about 4,000 of them developed breast cancer. So we've got this multifactorial prediction model, and we're layering in the genetic risk score, and we're saying, compared to the average risk group, which we've defined as the 40th to 60th percentile, how does risk of developing breast cancer, incidence breast cancer, change? So you can see that the lower the risk score here, the lower the percentile, an obvious decrease in risk of breast cancer. And at the other end of the scale, as we increase the percentiles, we increase their genetic risk, it increases. So that's in the full cohort of women. What about in the standard cohort that we defined after that kind of proxy for underwriting? Well, exactly the same trend, and very difficult to argue that there's any difference in that risk component, the polygenic risk score. If you look across the kind of percentiles by full cohort and standard cohort, it's pretty much identical. So potentially underwriting hasn't actually taken into account this genetic risk information, or it hasn't kind of filtered out those with high genetic risk or low genetic risk. And we also looked at cardiovascular disease exactly the same way, but now we're looking at men and women developing a coronary event and or stroke. And so here we've got 373,000 people. about 6,400 coronary events, and then on the right hand side we've done the same thing, but we've just filtered down to the standard cohort, so 261,000 people and about 3,500 events. And a similar picture really, if you look across the risk percentiles, we're kind of stratifying risk very similar, even when we've kind of underwritten or done a proxy for underwriting on these people. In fact, like you might sort of see here at the upper end that risk actually even looks possibly greater for those standard people at the higher percentiles. So food for thought for us. We thought, okay, this is interesting, and maybe not even what we were exactly expecting. So of course, then we were kind of interested. Well, if this really is very predictive, these polygenic risk scores, after controlling for all the things we typically would do in underwriting, how much the risk is there. So I'm just going to quickly point you to some of the research that's out there. There was actually a paper also has looked at polygenic risk scores that published in the Journal of Health Economics earlier this year by Linner and colleagues. And also I should point out the work that the Australian Actuaries Institute has done on the subject. So in May 2017, Vukachevich and Chen published their paper and did a great job of actually summarizing all the new stuff that was happening, including polygenic risk scores. And I'd say, apart from the work that they've done and a bit of the work that we've done, really all the attention has actually from other actuary bodies like the SOA and CIA has been on those monogenic mutations, those high penetrant mutations that cause disease like breast cancer and Huntington's, but are much rarer than common diseases are. So returning to kind of the results that we established, we had this situation for breast cancer where we said that risk is very much stratified by your risk percentile of the polygenic risk score. And we thought, well, actually, what if people were to purchase insurance that mirrored exactly their risk according to that genetic risk score? If that were the case, if people were to behave exactly that way, which we know people don't behave that way, and we know that this information isn't readily available yet, but if they did, what we would see is our risk pools would get skewed towards people with higher risk and skewed away from lower risk. And in that case, we'd see a 12.6% increase in incidence. Very, simple assumptions on the insurance seeking behaviors, of course. And just to contrast that with kind of your BRCA1/2 mutations, because only about 1 in 500 women have those mutations, yes, they confer high risk, something like 5 or 6-fold higher risk. But if you were to do the same experiment with that, you'd see a 2.2% increase in incidence. So it's very simple. I don't think people would behave this way if they had genetic risk information. So this second scenario is, maybe a better one in so much as what we do now is we suggest that actually if you're at lower risk, it wouldn't change your probability of purchasing insurance or your probability of purchasing more or less insurance. It would be a case of maybe those with higher risk might decide to buy insurance more frequently or buy more insurance. And in that case, what we've done, instead of mirroring exactly the genetic risk, we've taken half of it and said that probability of purchasing insurance goes up by a half. And in that scenario, again, very, very simple, but just interesting to see how the risk pool changes and how we get a 5% increase in incidence of breast cancer owing to this. So I will at this point head you back to Scott to round up the presentation.
So we're flicking between prezos. Okay, so I'd like to finish up by returning to, I guess, the questions that I posed just before I hand it over to Richard. and let's take stock of those questions. Okay, so the first statement was around genetic information not being that widely available in the near future. Now, I think given what we've shown today, I'm not sure you could claim with confidence that anymore. So we'll score out not. The second was around monogenic mutations that confer materially higher risk are rare, and hence cost to the insurers will be small. So I think out of all of the statements, this is probably one that is still reasonable, but with larger amounts of people undergoing genetic tests. For example, the BRCA genes, then this could soon become more of an issue. So we'll caveat that one. Number 3 was most common diseases are multifactorial, and genetic contribution to these is modest. So I think with improvements in polygenic risk scores that Richard just talked through, that will counter this one. And then the last two were around underwriting processes in terms of the clinical measures and also the family history. So I actually think the King's College London research is kind of throwing a lot of doubt into both of those statements. Now, I guess it's not all doom and gloom. Like advances in genomic medicine will undoubtedly improve disease diagnosis and ultimately disease prognosis, which will improve, I guess, improvement in life expectancy and improve life expectancy. So I guess the insurance industry, if we're able to look at this in the future, we'll be able to benefit from this as well as the general population. So one last bit of RGA continually do papers on genetics and amongst lots of other topics. So there's a handful. You can find these on the RGA website, but there's constantly new data, new research being thrown out. So if you're interested, have a look on the website. And with that, open up to questions.
Okay, thanks, Scott and Richard. I think that was a great presentation. It's explaining some very technical research in a way that even people like me can understand, and also talking about the relevance that it's obviously got to us in the insurance industry. So I've got one question at the moment on Slido, and I've got a couple of my own, but keep those questions coming in if you have them. So I'll maybe start with the question that we've got here from Zane. She's thanking you for the excellent presentation, but also curious what your views are on the fairness and also the consequences of ignoring genomic information. So I guess that's probably quite similar to where the FSC's landed on the moratorium.
Yep.
I think the microphone's working. If you want to.
Hello? I'll just stand here. Yeah. That's okay. I can stand here. It's on. Oh, it's on. Okay. Yeah. So I guess the FSC of fairness and
the consequences of ignoring.
So I guess the main thing for me is there an information asymmetry in terms of I guess knowledge is power. I guess the more data that's available for all parties will then ultimately lead to fairer outcomes for everyone. Some of the consequences I see of the information for not having that kind of sharing of information is, I guess, if people are anti-selecting against the whole pool, then ultimately the rest of the pool have to pay for the cost of that in terms of insurance. So premiums will go up, and there may be people trying to, I guess, but then the FSC have introduced, I guess, the moratorium, which tries to, I guess, find a balance where people can get cover without needing to disclose genetic testing, but they have a cap in there that will mean that there's not ridiculous amounts of cover being taken out. So I think the FSC are trying to find a balance. Like it's a difficult question to answer, but I think where they've pitched it seems kind of fair to me. The cover levels are meaningful, but they aren't crazy.
Thanks.
Richard, do you want to add to that, or?
Yeah, I'll add. It is obviously like a difficult subject, this, and it brings into question, lots of other concerns and ethical concerns and so on. I think actually one of the papers Scott had on screen there had a significant update from largely our CMO team, talking about some of these challenges in more detail. So that's probably worth a read. It was the middle paper that was on screen. But the other thing that Scott said that made me think is this balance is constantly shifting. So, as we've heard, the genetic tests are getting cheaper. So the balance of actually getting this information is constantly moving. So it is one that we just need to kind of monitor, because I think, the impact that we see in any anti-selection risk could be a slow growth, I would say, that again, we need to just keep a close eye on it.
Thanks. You may have heard a cowbell in the distance there. We're not in a field. That's a warning that we're just about to finish. I had a question for yourself, Richard. I thought it was quite interesting, the kind of idea of yourselves as a reinsurer collaborating with King's College London. Can you talk a little bit about just how that came about and potentially any kind of further work that you're planning in this space?
Yeah, thank you. So we definitely were monitoring genetics, and polygenic risk scores came up. Actually, Catherine's husband is an actuary, so it was a case of she'd presented at, I think, one of the Institute of Actuaries in the UK, and so we'd just followed up with her to say this is something where we would like to do our own research. The collaboration continues. We've kind of now continued to sponsor a PhD student. Our original project was a one-year project with a postdoc. But yeah, and actually RGA, we're actually pursuing something similar on wellness with the biobank. These data sets are a fantastic resource, but they're normally restricted to academics. So actually with the biobank, we don't get access ourselves to the data, but obviously we can see results and we can help steer the research. So it has been a very good partnership, really, I think, for both parties, because we've exposed them to questions that they ordinarily don't think about.
We've got a couple of questions coming in. Got one here from Maggie, and I think what this question is doing is maybe turning things on its head. So rather than necessarily customers selecting against insurers, the question here is maybe is a potential here that insurers could end up denying cover to individuals who currently would have access to insurance.
Well, not at the moment where there's the moratorium, so they can apply for the cover underneath those sums insured. In the future, I guess with more information, you could develop products for these people that are specific for certain conditions, and maybe do something there. I guess it just depends on being able to gather the data, and then I guess being a bit innovative and developing new products and see what we can come up with.
I'll add one other thing, actually, because we haven't had time to go into all the studies here, but it's very interesting that, that genetic risk isn't fate. We're not talking about that, obviously all these people are going to suffer in a disease in their lifetime. And there is an interesting body of work now that how do you kind of offset the risk there? And Kira and authors, one of the first papers that I mentioned on coronary disease and the twofold risk, they've looked at how lifestyle, exercise, and other habits kind of can offset the overall risk of someone getting coronary disease. So it's like all things, if we had more data to say, okay, well, they have high genetic risk, but they're exercising, they don't smoke, they drink in proportion, it's the bigger picture, but they have certainly, and others, shown for lots of these diseases that, again, it isn't fate here. And there is ways of mitigating that extra risk from genetics.
Thanks, Richard. I think that probably takes us quite neatly into another question that we got from Amanda, which is there seems to be more and more research suggesting environmental factors such as diet have greater impacts on longevity and healthfulness than necessarily genetic makeup. It sounds like potentially you agree with that.
Yep, and that's actually why we're pursuing another kind of collaboration. It's not with King's, but also with the UK Biobank, because again, I mentioned that it has all that information as well. So I didn't have on slide, but it does ask people about diet. It does do very detailed questionnaires for some people as well. So it really is the full kind of gamut of risk information that we could see in some way, coming to us and potentially being used for underwriting. So yes, yeah, it is a really interesting area, and I think there's a lot to it.
Cool. I think that's brought us to the end of the questions, which I think is neatly on time. So if you wouldn't mind just thanking the presenters in the usual way.